This project is my medium ISP, the ACES Smart Drone. It is a custom-built quadcopter control system using an Arduino Nano, electronic speed controllers, and wireless communication. The goal of the system is to control motor speed through a joystick-based throttle input and demonstrate a functional drone. The system is divided into two main parts, the controller and the drone. The onboard PCB is powered by a 3S 5200 mAh battery. That battery drives the power distribution board, which provides voltage to the four 30-amp speed controllers, which are connected to the four motors. The board also powers the Arduino Nano via a 5-volt rail. The controller was built on a breadboard using an Arduino Nano, a joystick module, and an NRF24L01 transceiver. The joystick provides an analog signal which is read through an input pin. A dead zone is applied around the center position to prevent noise and accidental motor activation. The joystick value is then mapped to a range of 1000 to 2000 microseconds, which represents the throttle signal sent to the drone. This value is transmitted wirelessly using SPI communication through the NRF24L01 module. Testing was done using the serial monitor to ensure that joystick movement provided stable and accurate throttle values. On the drone side, an Arduino Nano receives the transmitted throttle value through a second NRF24L01 module. This value is used to generate pulse width modulation signals that are sent to four electronic speed controllers. Each ESC controls the speed of a brushless motor, which produces thrust through propeller. The ESCs are first armed at a minimum signal to ensure safe startup. A fail-safe mechanism is also implemented so that if no signal is received, the throttle returns its minimum value to prevent uncontrolled rotation. During that testing, the drone consistently drifted to one side. This was caused by differences in motor output, small variations in hardware, and weight distribution. Another issue discovered was the incorrect use of identical propellers, which negatively affected lift and stability. To correct this imbalance, a manual trim was implemented in the code. This increased the power to the motors on one side of the drone while keeping the other side unchanged. The trim was only applied when the throttle was above the minimum value to ensure safe operation. This adjustment allowed the drone to produce more balanced thrust and improved overall control. The system was then transitioned to a custom printed circuit board designed in EasyEDA. The PCB integrates the Arduino Nano, radio module, ESC connections, and power distribution into a compact layout. Signal traces were done auto-routedly, and all components share common ground to maintain consistent operation. These significantly improved the organization and reliability of the system compared to my old breadboard prototype. The system did not have a working IMU-based stabilization after being soldered onto the PCB. This meant that it couldn't automatically correct its orientation. As a result, like I mentioned before, manual trim adjustments were required to maintain balance. Finally, future improvements for this project would include a few things. First, I would integrate an IMU to enable pitch and roll stabilization. This would allow my system to automatically adjust motor speeds, achieving stable hovering. I would also custom print a 3D frame for the drone to remove some weight. Thank you very much for watching my video of my ISP medium, the ACES Smart Drone.